In the year 2030, the United States is engaged in a conflict with China and Russia, with most of the hostilities occurring in the maritime environment. Beneath the churning waves of the Pacific Ocean, approximately 400 meters deep, the temperature barely exceeds freezing point. Inside the hull of a submarine, 134 sailors monitor a series of screens, illuminated by the reddish glow of combat lighting. Somewhere in these waters, a foreign vessel attempts to remain undetected. It doesn't stand a chance, because this is not an ordinary submarine, but a Virginia-class submarine, the supreme predator of the United States beneath the waves, and the most advanced underwater combat machine ever built. This marvel of American engineering has an impressive cost of $4.3 billion per unit, but offers capabilities that keep potential adversaries awake at night. However, the Virginia-class, which includes the USS Virginia, did not emerge from a vacuum. It arose from the ashes of Cold War submarine doctrine and the limitations of previous generations. Through the Virginia, the United States can maintain submarine dominance in a world where ocean depths become more contested every year. Let's take a deep dive into the evolution that produced this masterpiece of naval warfare and examine how the US Navy's submarine force remains light years ahead of its closest competitors. It is impossible to fully appreciate the innovations that transformed the Virginia into the submarine monster it is without understanding what preceded it. The Los Angeles-class attack submarines dominated the Cold War era. Fast, lethal, and with a total of 62 vessels patrolling the oceans, they formed the backbone of America's submarine force for decades. But by the late 1980s, their limitations became increasingly apparent. Soviet submarine technology was advancing rapidly. Akula-class submarines featured drastically reduced acoustic signatures, which threatened the United States' traditional advantage in submarine detection. This development sent shockwaves through the US naval establishment. The ability to detect enemy submarines before being detected yourself is the fundamental principle of submarine warfare, and it was at risk. The Seawolf class was the United States' immediate answer to the growing threat. Larger, quieter, and substantially more lethal than anything that preceded it, the Seawolf represented the pinnacle of Cold War submarine design. Its specifications were nothing short of astonishing. 8 torpedo tubes versus 4 on the Los Angeles, a drastically reduced acoustic signature, and the ability to launch Tomahawk cruise missiles. There was just one tiny problem. Each Seawolf cost an impressive $5.64 billion in today's money. With the collapse of the Soviet Union and shrinking defense budgets, the program was canceled after only 3 units were built. In the early 21st century, the Navy faced a daunting challenge. The Los Angeles fleet was aging and needed to be replaced. The US needed to do this without breaking the bank, while still countering evolving threats from Russia and an increasingly assertive China. Enter the Virginia class, a submarine designed not just for Cold War-style deep ocean duels, but for the forecasted multidimensional conflicts of the future, or present depending on how you look at it. The Virginia program began with an ambitious goal to create a submarine with 90% of Seawolf's capabilities at 70% of the cost. What emerged was something even more remarkable, a completely new approach to submarine design and construction. For starters, the Virginia became the first major US submarine designed entirely using computer-aided design. No physical mock-ups were created before construction began, which was a revolutionary approach that saved hundreds of millions in development costs. Every pipe, wire, and component was meticulously modeled in virtual space before a single piece of hull was welded. Traditional submarine construction required the boat to be built around the control room. The Virginia flipped this concept on its head by making the command center a modular unit that could be built and tested separately, and then installed as a complete package. This is not just a clever construction trick, it radically simplified upgrades, as the entire combat suite could be swapped out without cutting into the pressure hull. Speaking of the hull, a major change introduced to the Virginia was the removal of traditional periscopes. Of course, being able to see on the surface was still one of the crucial capabilities of periscopes, but they had a serious drawback. They created another hole in the hull that was sealed with less durable material than the hull itself, creating critical structural flaws. Enemies could target periscopes to sink or damage submarines. In fact, a total of 9 submarines suffered periscope damage during World War II. In the Virginia, these were replaced by photonic masts, essentially sophisticated digital cameras mounted on retractable stalks. These masts transmit visual data to high-definition displays in the control room, eliminating the need for a periscope. But perhaps the most significant engineering achievement was the Virginia's propulsion system. The S9G pressurized water reactor delivers approximately 30 megawatts of power, enough to propel the submarine at speeds exceeding 35 knots, without the need for refueling during the estimated lifespan of the vessel, approximately 33 years of operation. The absence of refueling not only saves money on expensive nuclear material that could be used elsewhere, such as in power plants or to create nuclear weapons, it eliminates lengthy midlife refueling overhauls that typically take submarines out of commission for years. As a result, a Virginia-class submarine spends more of its operational life actually at sea than any predecessor, delivering more capability per dollar spent. But being able to move quickly and over long distances will not make submarines survive a conflict. Submarine warfare boils down to a simple principle: whoever hears the other first wins. And in this deadly underwater game of hide and seek, the Virginia is designed to excel beyond any reasonable expectation. The boat's hull features an advanced anechoic coating, special tiles that absorb sonar energy rather than reflecting it to enemy sensors. This coating not only reduces the submarine's sonar signature, it actually gives the Virginia a smaller sonar cross-section than many smaller submarines. Additionally, the Virginia employs what engineers call acoustic quieting, techniques that minimize noise generated by the submarine systems. Every pump, every motor, every piece of machinery that could generate detectable sound is mounted on sophisticated isolation platforms that prevent vibrations from reaching the hull. The submarine's large aperture bow (LAB) sonar array represents another quantum leap in capability. This system uses advanced fiber optic technology instead of traditional copper wiring, reducing weight and dramatically increasing sensitivity. The Virginia can detect acoustically quieted adversary submarines at ranges that would have been impossible before its inception. Perhaps most impressively, the Virginia can maintain its stealth advantage even at high speeds. Its unique pump jet propulsor replaces the traditional propeller with a shrouded rotor that significantly reduces cavitation, which is a fancy name for the noise-generating bubbles created by conventional propellers. This means the Virginia can dive at maximum speed while generating less detectable noise than previous submarines would generate when trying to operate in silent mode. However, stealth means nothing without strike capability, and even here, the Virginia does not disappoint. The submarine carries a devastating array of weapon systems. 4 21-inch torpedo tubes can launch Mk-48 ADCAP torpedoes, guided weapons capable of speeds exceeding 55 knots with warheads powerful enough to open any surface vessel once launched. These torpedoes are essentially autonomous hunters, using sophisticated sonar systems to track and intercept targets without further guidance from the submarine itself. But what truly sets the Virginia apart is its versatility in strike missions. It has 12 dedicated vertical launch system tubes, allowing it to fire Tomahawk cruise missiles against land targets more than 1,600 kilometers away. Later, Block 3 and Block 4 Virginia models replaced these individual tubes with 2 larger Virginia payload tubes, each housing 6 missiles, which are loaded through the submarine's forward escape trunk. With the Block V upgrade currently entering service, the Virginia's strike capability is further expanded with the addition of the Virginia Payload Module, a new 25.6 meter section inserted into the middle of the submarine containing 4 large diameter missile tubes. Each of these tubes can accommodate 7 Tomahawk missiles, bringing the submarine's total missile capacity to an impressive 40 weapons. This transforms the Virginia from a hunter-killer into a true maritime strike platform, capable of launching the equivalent of a small air fleet's worth of precision-guided weapons from completely undetectable positions off an adversary's coastline. The submarine is not limited to conventional armaments. It can deploy Special Operations Forces, SOF, from a dedicated chamber called a lockout trunk, sending Navy SEALs on missions even while submerged. The addition of the dry deck shelter, essentially a hangar attached to the submarine's hull, allows the Virginia to transport and deploy specialized delivery vehicles, such as the Advanced SEAL Delivery System, extending the reach of Special Operations Forces far beyond traditional limits. More recently, the Virginia has been modified to deploy and control unmanned underwater vehicles, or UUVs, autonomous robots that can extend the submarine's sensing and weapon range without putting the multi-billion-dollar mothership at risk. These UUVs can perform reconnaissance, install sensors, or potentially even attack targets themselves, multiplying the submarine's effectiveness. In fact, the Virginia's weapon capabilities have become so formidable that some naval strategists have suggested they may be excessive for certain missions. But let's take an even deeper look inside the submarine to see what really makes it tick. Upon entering a Virginia-class submarine, you will immediately notice that it does not resemble its predecessors. The cramped, manually operated control stations are gone, replaced by what resembles a spacecraft command center from a science fiction film. The heart of the submarine is its control room, dominated by the submarine command system, a network of high-definition displays that can show sonar data, tactical information, navigation charts, and periscope imagery. Sailors operate the boat using touchscreens and joysticks, instead of the wheels, dials, and levers found on older submarines. This digital transformation extends throughout the boat. The Virginia is controlled by approximately 4 million lines of code running on a sophisticated fiber optic network. Every major system, from weapons to propulsion to life support, is monitored and controlled through this integrated digital architecture. What makes this remarkable is not just the technology, but how it transforms operations. Traditional submarines required dedicated watch standards for countless individual systems. The Virginia's automation allows it to maintain approximately the same crew sizes as the previous Los Angeles-class submarines, while having significantly greater operational capabilities and being overall larger. On the other hand, this automation placed a bit more stress on the crew. The Virginia needs fewer sailors overall, but those it has must possess advanced technical skills to maintain and operate its sophisticated systems. Additionally, submariners must still adhere to the US Navy's heightened standards due to long periods spent underwater and in relative isolation. Another revolutionary aspect of the Virginia's controls is the fly-by-wire control system. Traditional submarine control surfaces were hydraulically actuated, physically connected to control stations by mechanical linkages. The Virginia replaces this with a digital system where computers interpret operator commands and translate them into movements of the rudder and diving planes. This not only improves response time, but allows for unprecedented maneuverability. The Virginia can execute maneuvers that would have been physically impossible for earlier designs. Digital transformation also extends to crew comfort. Due to its larger size and reduced machinery requirements, the Virginia offers each sailor more living space than previous submarine classes. Bunks have reading lights, privacy curtains, and personal storage. But ostensibly, the main changes concerning the submarine had to do with how it is operated and used by the US Navy. Cold War submarines had a relatively simple mission: hunt and destroy enemy submarines and ships, remaining undetected. Virginia was designed for a much more complex strategic environment where literal operations, i.e. as near coastlines, have become increasingly crucial. This shift in focus drove numerous design changes. The submarine's sail, the fin-like structure on top of the hull, was designed to withstand the stress of breaking through Arctic ice, allowing operations in regions that are becoming increasingly contested as the Arctic becomes a more likely option for trade between East Asia and Europe. The bow sonar sphere found on previous attack submarines was replaced by a horseshoe-shaped array better suited for detecting quiet diesel-electric submarines operating in noisy coastal environments. Virginia's shallow water capabilities are particularly impressive. The submarine can operate in waters as shallow as 90 meters, dangerous territory for nuclear submarines, which generally prefer the safety of deep water. This allows it to collect intelligence, insert special forces, or launch attacks from positions inaccessible to previous generations. These capabilities make the Virginia a master of what naval strategists call access denial missions, the ability to operate in areas where surface ships would be at extreme risk from enemy weapons. During hypothetical conflict scenarios, Virginia-class submarines could penetrate heavily defended waters to eliminate crucial enemy capabilities, paving the way for larger naval formations to enter the battle space. But perhaps the most dramatic expansion of the Virginia's mission set occurred with the retirement of the Ohio-class guided missile submarines. These converted ballistic missile submarines carried up to 154 Tomahawk missiles each, providing massive conventional strike capacity. As these platforms began to be decommissioned without direct replacements, the Virginia, particularly Block 5 with its Virginia Payload Module, stepped in to fill this capability gap. The Virginia also took on expanded intelligence gathering roles. Its advanced electronic warfare suite can intercept communications, radar emissions, and other signals of interest from potential adversaries. The photonic masts can capture high-resolution images of coastlines, naval bases, or vessels. A particularly valuable capability is the Virginia's ability to tap into undersea communication cables, accessing the digital nervous system of global communications in ways that are virtually undetectable. In essence, the Virginia has transformed from a specialized anti-submarine platform into a multi-domain combatant capable of shaping battlefields across the spectrum of conflict. The Virginia program also pioneered a unique construction approach. Each submarine is built modularly, with large sections built simultaneously at two different shipyards: General Dynamics Electric Boat in Connecticut and Huntington Ingalls Industries in Virginia. These modules, essentially fully equipped sections of the submarine, are then joined in final assembly, drastically reducing construction time. This approach solved a critical industrial challenge. After the Cold War, America's submarine industrial base had atrophied significantly. Production rates had fallen from several submarines per year to one every few years. Skilled workers were leaving the industry and supply chains were disintegrating. The Virginia's construction method allowed the retention of critical skills at multiple facilities, preserving the specialized workforce essential for submarine production. This also reduced the cost per unit from $8 billion for the first boat to approximately $2.4 billion for recent blocks. The subsequent remodeling and addition of more armament increased prices again, but the initial price reduction was still a notable achievement for the U.S. military-industrial complex. The Virginia was not designed as a static platform. From its inception, the program incorporated planned capability upgrades divided into blocks. Block Y, USS Virginia to USS Texas. The original configuration establishing baseline capabilities. Block 2, USS Hawaii to USS Minnesota, introduced cost reduction measures while maintaining capabilities. Block 3, USS North Dakota to USS Delaware, replaced 12 individual vertical launch tubes with two 87-inch diameter Virginia payload tubes, each containing 6 missiles, reducing costs by $100 million per submarine. Block I-4, USS Vermont to USS Utah, focused on reducing maintenance requirements, increasing the number of deployments each submarine can conduct from 14 to 15 over its lifetime. Block V, USS Oklahoma to USS Massachusetts, added the Virginia Payload Module, a 25.6-meter section containing 4 large diameter missile tubes that significantly expand strike capacity. Each block represents not just minor adjustments, but substantial capability enhancements. Block V submarines, for example, will displace 10,200 tons compared to 7,800 tons for the initial boats. A 30% increase in size that brings corresponding increases in capacity. Construction innovations were not limited to management techniques. Block 2 introduced a newly designed bow that replaced expensive spherical sonar arrays with the more capable large aperture bow array at a lower cost. Block 3 implemented a redesigned stern with a hydrodynamically optimized shape that improves both stealth and handling. The result has been dramatic. The first Virginia-class submarines took 84 months to build. Recent deliveries have required only 61 months, with a goal of 55 months for future boats. For comparison, the nuclear aircraft carrier USS Gerald R. Ford took almost 2 decades from keel laying to commissioning. Even so, Virginia submarines are facing some challenges. By some estimates, the ships are technically being built too slowly. More recent inflationary and supply chain challenges have halted construction work. From what should have been 2 submarines per year, the US government has ordered an average of only 1.2 per year since 1998. For example, only 1 submarine will be ordered in 2025, and it will have the highest price yet at $4.8 billion. Additionally, the US technically promised that it would deliver 3 of these submarines to Australia by 2038, as they would form the bulk of the latter's modern submarine force and curb China's position and ambitions in the area. These submarines are unlikely to come from the existing supply, but rather from the fleet of submarines being built for the US Navy itself. Along with the general supply challenges, some critics estimated that the entire program is decades behind schedule and would require significant correction to align it with initial projections. This correlates directly with changing threat environments. China's rapid naval expansion, including sophisticated submarines like the Type 093G Shang class, has created new challenges for American undersea dominance. Russia, despite economic constraints, continues to produce advanced submarines like the Yasin class that feature dramatically improved quieting technologies. But even if the US does not have the quantity of submarines it should have by now, the Virginia is making up for it in pure quality. Its aforementioned modular design allows for the rapid integration of new technologies without requiring entirely new submarine designs. Digital architecture can be updated with new software, similar to how a smartphone receives operating system updates. Weapon systems can be modified to counter emerging threats without extensive reconstruction. The program has even addressed life cycle costs. The newest Virginias require only 3 major maintenance periods during their 33-year service lives, compared to 4 for earlier blocks, drastically reducing downtime. And while the Virginia represents the current pinnacle of submarine technology, the Navy is not sitting idly by, waiting for production to catch up. Development is already underway for its eventual successor, the SSN-X program. Preliminary reports suggest that the SSN-X will be significantly larger than the Virginia and 11% larger than the Seawolf. The increased volume technology propulsion is electric signature. The Navy is also investing heavily that will work in conjunction in submarine. Programs like the Orca Extra Large UUV aim to create autonomous underwater drones capable of mine countermeasures, anti-submarine warfare, and electronic warfare. These could multiply each submarine's functionality without requiring major overhauls and upgrades to the vessel itself. The Virginia program continues to evolve. Block 6 submarines, still in the planning stages, may incorporate technologies from the Columbia-class ballistic missile submarine program, including the advanced X-stern configuration that replaces traditional rudders and stern planes with a single set of 4 multi-purpose control surfaces. So, where does the Virginia-class submarine fit into the context of present and future threats to US supremacy? While it is difficult to directly compare the theoretical capabilities of China's vessels, as most of these updates are kept under wraps, the Virginia is believed to still be ahead of the pack. It can be deployed near an adversary's coastline for months without detection, gathering intelligence, mapping defenses, and positioning itself to deliver devastating strikes if conflict erupts. Its mere presence establishes a zone of both maritime and land superiority, as potential adversaries are compelled to assume it can be anywhere, at any time, forcing them to allocate valuable resources to submarine detection and defense. And even if future conflicts may involve hypersonic missiles, artificial intelligence, and space-based weapons, the fundamental advantage provided by advanced submarines remains unchanged: the ability to operate with almost total impunity in contested environments, striking when and where enemies least expect it. After all, there is much more of Earth below the surface of the water than above it, and the ocean is much less monitored than the land or space. With each new Virginia that dives into the water, the US strengthens its most decisive military advantage: the ability to strike anyone, anytime, and without detection or response. But what do you think? Is the massive investment in these underwater predators worth the price tag? Or should the United States focus on other domains of warfare? Leave your thoughts in the comments below.